Я вам там тогда документик перешлю для них, чтобы у них был при нотусе прикреплен задание, что делать. Они удаленно, получается, будут?
Да. Прибегут, они потом пересматривают.
Доска нормально будет выглядеть, если как-то не блокует?
Нет. Ничего.
Распишите.
can be done in 3 minutes. No. Mums viss izņemot. Naval receiver. This one is called naval receiver. Also a receiver for ships. Shortwave receiver. Then you need
They get some radar or something.
no, it's it can be part of radio communication. Key when it was used weather forecast. Daily weather forecast.
Now they have much more red ones.
Yeah, but this one is still designed as a historical item, and often used by I think what to do with them. Abandon, put there, put somewhere. Get them out. Will someone appear? What's online? No one.
You can take all together.
No, it's not a very good idea. Better. Let's see when this is going to be. Я aussi писать? Yes, this. No one online. They are 6 minutes behind the schedule. В каком месте? Use the kit. field jacket. Where this comes from? Beijing.
It can catch so far.
They have powerful transmitter. But this thing is for really for long range communication. Really.
And someone need to pay for a powerful transmitter as well.
Yes, this big government monster eating. If it can emit 800 kilowatts, Mr. Xi to pay for approximate, just below 2 megawatts of power.
Okay, I think we could start.
Yeah. Second.
Mm-hmm.
Morons took a coil from the coil. I have spare one, but it's the last one. It's my last one. Okay, let's switch. Oh, I can make it bigger. Where we are.
Question is about the quality. Is it okay?
We can enlarge it.
Resume.
Now it's fine.
Okay, let's see. Focus. Okay.
Okay.
Was better? No. Yes, stop. Too much.
Bit enlarge.
Up. Yes. No. Good. One small step back.
This direction.
No, wrong. Yep, stop.
Yeah.
Good. Now, this you can do. So we could start for today. What is our task? Today we will start some practical tasks because
Maybe I can change heading
maybe
because we.
relay protection.
It's okay,
It's
no
okay,
lecture.
but it's not a lecture. Maybe
But
let's
it's-
switch it to the practical tasks.
Yeah. Hey, come on.
Practical tasks for your homework. First of all, because every student won't have a grade. And it means that you need to do something by yourself.
Here.
This lecture is missing, but we need something more. Okay, so once more time. Today we start practical tasks for your homework. So this homework is important because you want to have a grade. That's why please follow me if anyone is connected online. And if you have questions, please ask. So, okay, so for the very first task, because we will have several tasks, I'd say several simple tasks, but we need some practice to understand at least how to build equivalent schemes or sockets by yourself, how to calculate protection set points, and how to design your protection. So, very first task is for selectivity. So we have a radial network, distribution network. Very simple. Here from the left, let it be from the left, is a source of power, concentrated, yes, and we have radial lines, series lines. Every line has its own protection. So here we have numbers 1, 4, 5, 6, 2. So total number of lines 6, yes. And the current protection is the same. We have 6 current protections for every line. And we have loads, multiple loads, yes, with Roman digits, no, Roman letters, yes, so from 1 to 14. And what is the selectivity? What's your opinion? What does it mean, selectivity? How do you understand this issue?
It's like a source and different transmission line with respect to their different loops.
Somehow. The main idea is we need to make the right sequence of protection operation. So, if, for example, this is why we choose this example for you. Because what do we see? Here we got lines in series. It means that we have the same logic for the loads. So we have loads in series. And in case if we have anywhere a fault and we will disconnect power switch number 1, which one is located on the line number 1, it means that almost every load will be without the electricity, will be disconnected from the network. Is it good? No. It is not good because, for example, if we have fault, like, for example, it is here T2 in the place, yes, why do we need to disconnect line 1? It is enough to disconnect the switch, power switch number 3, yes, to isolate the fault from the grid. So what is the idea of our protection? Because the very first question for the protection design is who we are protecting. We are protecting the load or we are protecting the network. If we are talking about line protection, we want to protect our network, our lines from a fault. That means we need to isolate our network, our distribution yes, from the element, the fault element. For example, this is line number 3, yes, in this case. So we need to isolate our network from this element. In this case, okay, we understand this issue, but how could we use to switch off our power breaker number 3? Or circuit breaker, yes, circuit breaker number 3. If we, for example, disconnect circuit breaker number 2, it means that we will lose the load number 5 and number 6 as well. Is it good? No, it is not good. That is the question about selectivity. Who is the first, who is the second, who is the third? So who must operate first? And in this case, we have one more question based on this topology. Okay, the first to disconnect is number 3. But do we want that, for example, other protection in series number 2, number 1 could detect this fault? Yeah, there are two logics. The first one is to detect the fault. Because if the protection device can't detect the fault, it can't send the signal to disconnect the circuit breaker. And in this case, we separate two definitions about to detect and to send the signal to disconnect. Because if we send the signal to disconnect, it means that we are disconnecting. But there is a time delay from the moment when we detect and we send the signal. Because in this case, current protection 1, because they are in series and we understand the fault current is in line 2, in line 1, and in line 3 as well. Yes, because this is our direction from the source, power source. So, we have the fault current. And in this case, do we want that current protection 1, current protection 2 detect this fault as well? But no, you say no. But in case if we have any problems with circuit breaker number 3 or with current protection over current protection, to be clear, yes, number 3.
Can really number 3 should detect it?
Primary, yes. But we want to reserve, we want to have a possibility, yes, to disconnect the fault element from the grid with other devices.
Backup operation.
Yes. In other words, backup operation. Because you see, fault is very dangerous from the network. Many reasons can appear with our protection or circuit breaker. But we need to be sure that the fault element will be disconnected. In any case. That's why when we project design, okay, when we design this, because this is very simple overcurrent protection design, we make that all current protection in series could detect. So we calculate, we select such current protection set point for detection that all protection in series could detect this fault. But we want to make that the current protection number 3 will operate first. How we could make it? Using time delay. So, the main tool for selectivity. So to make this sequence, who will be the first, who will be the second, who will be the third, and so on, is possibility to use time delay for operation. So all relays in series could detect this current, but command on iteration, on disconnection, yes, will be for the relay number 3. First, second, and third. How we could make this? Using time delays. So, put time delay here. Oh, okay, it could. Of course, it depends on our possibilities. What will be the selectivity step? So we could think that if we know that in this branch, this is the last in series, yes, protection, so we could put time for operation 0, and every next in this branch, yeah, this, oh, okay, I call this all one branch, yes, and this is lines in series that make this branch. So we'll have the time delay more for a time for selectivity step from the last point. So number 2 plus time step, number 1 one more time step. So in this case, if we put the time delay for relay number 3 0, for relay number 2 taking into account time step half a second, we'll have the time delay half a second. And for the line number 1, yeah, 1 second. So in case we have troubles here, of course we will wait, yes, but this design makes that by the end we will disconnect the fault element, yes, but we have here two branches in parallel. So it means that, okay, if we calculate on this side and put the time delay for relay number 1 second, maybe we'll have problems with the second branch in direction 1, 4, 5, 6. In this case, when we start design for this branch, so the same logic, we could put 0 here, plus time step half a second here, 1 more step here, so 1 second here. So 1 second here and 1 second here, not good. So it means that when we have parallel branches, yes, we use the maximum time. For this reason we will relay number 4 and plus delta t, plus time delay. So it means that what will this time delay for relay number 1? 1.5. Yes, 1.5. Very simple. Very simple and very simple logic. But in this case, we design this selective operation. So, and here is your task for homework. So you need to select for every here is transmission line, but this is more close to distribution network, but whatever. It depends on your voltage, how we call this, transmission, distribution, and so on. So you need to select, as is written in your task, yes, time delay, so T1 to up to 6, yes, for every line. And here is a table with time delays for a local load protection. So as you understand, every consumer, every load has its own overcurrent protection as well for their purpose. And here they have operation time. So it means that we need to calculate, taking into account that here, all ends have their own time delay. So it means that 6 will be not 0, but 6, 6 time delay depends on time delays of the load protection is 13 and 14.
Like these are the base time of the loads, and then we need to add for every relay.
Yep. Yeah, because for loads you have, and you need to select time delays for
Can you
overcurrent
show
over
us example?
line overcurrent protection.
Can you show us example of any of them,
Sorry, what kind of example?
of resolving it? Any of the one?
We just discussed this. How this can
Like
be.
if I say for load 1, load 1 is not in the series.
Load 1 is yes, consumer load 1, yes. Load 1 we see in the table, it has time delay 1 second.
So it will be only 1 second, right? Because it's not connected to any
so-
of the relay.
It is set 1 second because it is in the table and you don't change these sets for the loads. As it is written in your task, you need to select only current protection for lines 1 to 6. And you understand that this is also, so this is land. Yes, this is it's the last, the only one element in this branch. That it means that you don't need to take in account this delay when you're calculating this parallel branch time delay. So you need to make a table with times, time delays, and okay, maybe 2 columns. Set point, 1 column, no, one first element, and the second column is formula. How many time steps do you use? Yes, for these relays to be clear your logic. So this is very simple task. Okay, I think we could go next. This is very key. The second task is more complicated, but you need to calculate set points only for 1 protection. Okay, here you see the name of overcurrent protection. It is MSA. It is in Latvian, but we call inside red an overcurrent protection. So I just keep this name. So you have here current protection MSA. So okay, what do we see here? What do we see here? So power source, 2 line number 1, line number 2, and feeders. Okay, if it's transformer and fuse, yes, you see transformers and fuses. What do we know about this network? Okay, we have information about this feeder transformer power, kilovolt amps nominal voltage, high voltage, low voltage, load value, and yeah, full impedance, yes. Impedance for the, okay, so transformer number 1, 2, 3. Okay, 1, 2, 3. Okay, we have 3 transformers, but they are the same. All are equal. 2 lines. 2 lines. What we know about lines? So we know the resistance and the reactance. So for 1 kilometer.
Yeah,
You
1
see?
kilometer.
1 kilometer, yes, 4 kilometers. The same is for the line 2, and we know the fault current value. So for this task, you don't need to calculate this fault. Okay, so we know the fault. this is maximum fault value. Otherwise, you need to calculate. Okay, this is for another purpose, but okay. We'll come back to this. And nominal voltage. Nominal voltage for this system is 10.5 degrees. Okay, this is what we can do. To calculate current protection set point, so first of all we need current set point, we need the formula. How to calculate this. And here, next. First of all, this equivalent scheme, for you to be easier to understand how to calculate currents, yes? So we simplify this network. But for the very beginning, I'd like to start with current protection set point. Okay, what is the main? First of all, we calculate current protection set point taking into account maximal current value, maximal load current value, multiplied by a coefficient. Now we will discuss about this coefficient, but first of all, about the maximal current. Yes. How do we understand this maximal current? Okay, this is your scheme. What is a maximal current?
Current used by the load
Yes.
relate to break the circuit.
Sorry?
The limit of current or the maximum current used by the load,
Yes.
which
Yes, by the
takes
load.
us to the circuit breaking point.
Maximum current of a load. Yes, because circuit in this scheme, we don't have
Circuit.
yes and its parameters. We have uses here only in scheme, what we can see. But when we talk about the load, the maximum load, current load value, here you can see the value from transformer. So what current could be for our load from the transformer? Because in our network, transformer is the main limiter, because our loads are loads connected to the transformer. Transformer has its limits, and it means that we could calculate that transformer limits are the same as maximum possible load limit. Because you understand the load number can be changed and so on and so on. But just okay. start step by step. Step by step. Row calculation. Okay, so maybe I will show you two documents. First of all, you will have for your home class this document. Yes, sorry, not this one. This one. You will have this one. And here, for you to be easier, you have several steps. What do you need to calculate to be easier? And formulas. Some typical formulas. For example, the Ohm law, or how to calculate transformer current if we know the power of transformer. The maximum possible power current from the maximum current from the transformer power nominal. So in this case, but for now, as we're talking about how to do, I will use the second document with values. Okay, so first of all, we start with the equivalent scheme. So we replace lines with equivalent reactance, transformers for reactance or impedance based on one parameter to be here, because we understand that there is a huge difference between resistance and reactance for transformers. So that's why very often we could use only the reactance, not the impedance for the transformer. So first step, we calculate nominal current for transformer using the Ohm law. Very simple. When we know the transformer power, we have nominal voltage and the Ohm law. Then here we have parallel transformers. For the first branch, we have two transformers. For the second branch, we have three transformers. That's why if we want to know the full current, we need to solve it. Very simple, because they are parallel in each branch. That's why we have this solve. Okay, here we go. We got the current value, transformer current. What is the next step? Next step, let's calculate what resistance, what impedance do we have for our lines to calculate for fault current. So, sorry, the first step is to calculate for this transformer. Okay. Here it's very simple because we know transformer impedances. That's why if we need, we just, if they are in series, we just can sum this. And next step is the line resistance, reactance, and impedance calculation. Again, very simple, and you have these steps. So line resistance, reactance, and impedance calculation. What do we need to calculate? Next step, maximal operation current. Well, this maximal current, okay, we define this as the maximal current depends on the transformer. Maximal current, yes. So that's why we just multiply this maximal transformer current with a coefficient. To avoid different sources and so on. And the next step is to calculate the fault current value, the on law. Okay, this okay, now we got everything what do we need. One very important moment. So if we calculate this fault value, what is that value? What is the full impedance? This is quite important moment. So because for fault calculation in this type of network, formula is very simple, but based on where do we put the fault, the impedance is the full way from the source, where, no, not from the source, from the place, okay, yes, from the source till the fault location. So that's why we need the right name of the impedance, what is that, and the right values as well. Okay, the right value as well. Okay, so the next question is, okay, if we calculate this fault current value, first of all, what is the location for fault for this network? And why do we need to calculate fault value? Because this is step by step. But as you saw in the current protection calculation, set point calculation formula, we don't have a fault current. Yes. But we have in our to-do list fault calculation formula. Why do we need fault calculation? Fault current value, why do we need this fault current? What do you think? And maybe the one more question, why we don't have fault current values in our overcurrent protection calculation formula. So if we don't have this fault current formula, it means that set point is not dependent on fault value, yes. If it is formula, it means that it depends on it. So why? The answer is in the basics of current protection philosophy or logic. Because what is a current set point? What is a set point? Is if the current is greater than the set point, it means that we understand that there is trouble, there is a fault. So this is, how to say, the criteria for a relay to understand, is there a fault or not? Do we need to operate or not? This is a criteria. Set point is to understand how to detect is it a fault or not.
Yeah. And then if we find the fault, then we need to find the current outflow.
No. Current value says, do we have a fault or not? So that's very simple. So because the relay task is to operate in case of fault. Yes. If you don't need to have a fault, everything is okay, and our life is perfect. So the main task is to detect a fault, and if we have a fault, to make the right operation to disconnect the fault element. Yes, fault. But we don't have a fault current in this formula. Why? What is the logic? What is the main idea? So if our operation logic greater than set point. So if we want to make a safe detection, I'd say, we need to choose a very low current set point. Because current could be different. Current value could be different. There are many issues why fault current values could be different. But we want to be yes, set point is our detector.
Yeah, it's
Yeah, it's a detector. And if we have a low set point, in order to be more correct, we want to have the lowest possible set point. Because the lower set point we have, the more safe we are. In this case, we want to have the lowest possible. This is from one side. But from the other hand, what is the lowest possible current value? 0. But we can't have set point 0 because if we don't have a fault, we have a normal operation current. So everything is okay, and relay must understand that we don't have any current. That's why in formula we have this maximum operation current, and we have a coefficient to make the set point greater than the operation current, normal operation current, yes? To be sure that in a normal operation, relay will not detect this current like a fault, because there is no any fault. So in this case, we choose the set point based on the value of the normal operation current, yes, because we want to have the lowest possible set point. This is from the one hand. But from the other hand, yes, we want that our detection, that fault current detection, is good enough. That's why protection. current search, and so on. Current protection set point using this formula could be not enough for this sensitivity, possibility for relay to detect the fault current. In this case, anyway, we need to check, is current relay with such a set point could detect the fault current or not. So, once more time, the logic is very simple. We want to have the lowest possible set point to be sure that we will detect the fault current. But at the same time, we need to check and to see how this relay will operate when we will have the real fault. Of course, this is paper, this is just calculation, we don't have a real fault, but we could calculate the real fault current value. That's why the last step is to check our set point. Is it good or not? That's why we need to find the fault value. But the current fault value, very, very clear. But let's come back to this. Let's come back to this original scheme. Okay. The definition to be sure that our current protection could detect fault current. But as we just discussed, fault current value depends on the fault location, because it is very simple, the Ohm law. We divide the voltage to the impedance from the source till the fault place. Fault could be very close with a very small impedance, or far away. It means that we will have greater impedance. Greater impedance, lower fault value. I think this is clear. And in this case, the question is, what fault location should we choose? Because we just discussed, okay, we have this current protection of line 1. All what we have done previously is to understand what is the maximal possible normal operation current for line number 1 to calculate over current protection set point. It is clear, okay, but we want to check and we want to make a fault to calculate the fault current value. What is the location of fault? What fault we will check? What fault location we will choose?
Transformer which have higher impedance,
You say transformer. We have 5 transformers
which have higher impedance.
which have higher impedance. Transformer with higher impedance. Higher impedance, it means that we will have,
The fault.
yes. But in this case you are right, but you're right, but not right as well. Of course, okay, transformer. transformer impedance, but on the impedance from the source, okay, I'm waiting the reaction from your side. So, from the source, from this side, yes, and which point? Whatever,
Yeah,
or
it can be in with the
why, for example, okay, I just try to how to say to move your ideas. Why number 3? For example, why you ignore number 1 and number 2?
no, R. So
But what does it mean far?
the name of the line, it's given like 2 kilometers.
We have a formula for whole population. Impedance from the source till the, who said that impedance of, who say that impedance, if you calculate this one with this one, with this one is greater than this one plus this one? Yes, that's why. That is why we are not saying that the fault location must be in place of transformer number 3. We say in a way of greater impedance. How could we know where is this? We need to calculate. So we need to calculate this branch, and we need to calculate this branch as well. And then we could compare. And the choose, as you said, because your logic is right, yes, the lowest fault current value to check. Okay, we have the calculation result. We have the current value, and we have a set point. For example, we have set point, for example, 100 and fault current 150. How could we understand is it good or is it not good?
Set current is 100 and fault current is 150.
Yes. This is the next question. Just analyzing. Like this, we have some formulas, we have some logic, but we have two values. How we could analyze situation? Because formula is a very good thing, but we need to understand the main idea, the logic. Why do we do this? So we have fault, we have set point. How do we understand, is it good or not? Yes, we have special criteria. We call it sensitivity. Is it enough sensitive or not? But how we evaluate? Okay, sensitivity is very simple formula, so we need to divide our fault current by the set point, and we will have this coefficient, so 1.5. So 150 divided by 100, 1.5. But is it good? Good enough. How could we evaluate it? Okay, yes. So we need any tool to understand. So this is not as simple. There is no simple answer about the sensitivity, because as we understand, the greater sensitivity we have, the better. So, because it is very clear, if we have a fault value of 1000 and a set point of 100, we could be safe that if such a huge fault current appear, relay probably will detect it, because there is a huge difference, yes, between the set point and the fault value. But what is the minimum possible sensitivity that is good enough for us to be safe?
Maybe double. Maybe double.
There are different sources with different opinions, different values. So I said this is not a very simple question with a very simple answer, but we could say, for example, for this simple distribution network, we could keep about 1.3, about 40%. So 130.
Very good on the very good scale. Above 1.2, okay, it's gold. Above 1.2,
Yeah.
20%
Not
is
less,
that.
not less.
Comparing to its ratio between your protection trip color and minimum possible fault color. If you have factor of sensitivity above 1.2, it's okay. It's below, in general, it's not okay. In theory of corruption, if guy on inspection end is your good friend, you're in good relation, for example, you're in good relation, and it's not a month of quality fight, you will go with 115, but it's a bottom line. No one sane will sign project if you have sensitivity below 115 for overcurrent protection. It's a law, no one will risk his head.
Sometimes it is quite complicated, yes, to make better sensitivity. As I mentioned, because it based on this construction, this network construction issues, yes, so this impedance of line and so on.
See, the problem may happen. You may be, how to say, the last in the global line. What can happen? When design starts, design of network starts, some need to check for, one moment, for equipment, will equipment withstand fault currents? For dynamic and thermal stability of equipment, will this primary equipment survive major fault? And what may happen? They can push up system resistance, artificial, to make equipment go. When it's on a brink, once, if you see things like calculus of connection resistance, account for active resistance of any element, they are pushing expected fault current down. When you design your protection, this may mean that real current will be higher, but your calculated current is lower, and you may be on the brink of sensitivity. Actually, if it's, you see, okay, this happens on the brink of sensitivity, you just change design, you use not simple overcurrent protection, but overcurrent, for example, negative sequence enable overcurrent protection. This will give you huge, really huge gap in sensitivity. If you, between financial wall and they are pushing current wall because they need to push the equipment below line, you're in trouble. So, common things start to happen. They push the equipment, you push your currents.
And at the same time, overcurrent protection is not the same. Like overcurrent protection with possibility to activate this sequence.
Yes, negative sequence activate.
Yep. Because, okay, current protection is a digital device, yes, and you could buy very advanced device, but the price is very different. Because it could be the same, but without possibility to activate, like direction protection, this sequence and so on.
You know where the talk is digging? Terminals without voltage section are much cheaper. At the moment you need this negative protection logic, you need voltage circuits. With terminal without voltage, all this voltage section is cheaper. So you need more expensive terminal, how can you? We don't have any money. Blah, blah, blah. Push them hard. Push them. Because it's small investment, but it can save huge money. So you also need to be aggressive on funding.
Yep, let's come back to this criteria, like sensitivity and so on. So yes, like Professor just mentioned, so the lowest possible it must be more than 1.2. That's why we choose 1.3. This is a very simple example, so not problem to have 1.3. So not to use this lowest possible. Okay, so in this case, one more. What do we need to do? We have this group of coefficients. That's all together is about 1.1, 1.3 as well. It depends on different issues, like what type of load, for example, do we have about this inrush currents. For example, very simple example. For example, if we have one very powerful circuit breaker at the for the load, and if as you know, electrical machine has a recent rush current surge as a first moment. That's why this coefficient could be different. That's why we could replace these three coefficients by 1.1, 1.3. Yeah. For simple network, use 1.1, sometimes 1.2, but 1.3 not very often. The most popular is 1.1.
Actually, in all books,
Mm-hmm.
be careful, you know that to be careful. The more, the richer customer, the higher will be this rate. Why? First, rich customer can allow air conditioning. Air conditioners have high inrush current. Second, lighting. LED lighting, this modern ballasts, they have DC stage at input. This charge of capacitor in DC stage gives you high inrush. Next, rich customers do have water pumps for the jacuzzis. And of course, industrial, the higher, say, level of industrial load, the higher will be inrush. If it goes at 20% for inrush. Good news, what you don't need to adjust for instant inrush. You need current at your protection stage delay point. And all these DC stages, they do charge quite fast. Long inrush are expected. Large water pumps, real large irrigation pumps, and higher inrush and in long air blowers for mines, very large air blowers. They start short, they start in long manner because they have high levels and they start with high current. So if your customer is a gold mine, take a high voltage.
1.3 at least, yeah.
The best place to once take a network analyze and record the network. You know, they can be tricky. Old in mineral areas, old oil crushers. They are starting painfully long. Some of its manual, even manual startup sequence, large megawatt class. They are still operational because these crushers and mills are very expensive. I saw, okay, I don't saw them in person, I saw them on videos, but appears what they are from times of industrial revolution, very old. 6 kilowatt motors and ouch, what a museum. Real running museum. They are very expensive and their owners are sharks of business. Prepare, they can make your day a bit harder. Okay.
Yeah, and maybe once more time to highlight why we're talking so much about such a coefficient. Because we need to have the lowest possible set point. And the lowest coefficient we have, the lowest set point we have. But on the other hand, we could have trouble, we could find a trap when we detect this start in rush current like a fault current. And we will disconnect all these loads, yes. All these rich people will be disconnected. And we will have troubles for this, for disconnecting them. That's why, yes, we're talking about what the digit is after the dot. So 1.1 or 1.2. Small difference, but could be quite important. Okay, this is all for your second task. I think today it's enough.
We need to find for all the three.
This, okay, so first of all, this document contains 3 tasks for you for your homework. Yes, today we discussed how to do the first task, very simple, with the time delay, just to understand the idea of selectivity. The second one, this is for the current protection. This is for you to understand, no, first, okay, to make the very simple equivalent scheme. This is quite easy. This is not the main idea of this task. The main idea is for you to calculate by yourself the set point and to analyze, is this set point good enough or not, using this sensitivity criteria. So for you to think about what is the location of fault should be chosen for sensitivity check. To analyze this sensitivity coefficient, is it good enough or not? To understand what is the maximal operation current and how this could be calculated based on knowing data about this network. So this is for the second task. We just discussed this. And the last task, which is here, we will need much more time about this because this is about to have practice in equivalent scheme design. Because here we don't have the radio network, here we have a loop. And for loop, to calculate fault current, not so simple, like using one simple formula. This is much more complicated. And the first step to calculate fault current for the loops, we need to make the right equivalent schemes. And this task number 3 for equivalent schemes. Because you need to make this positive sequence scheme, negative sequence scheme, zero sequence scheme, and to connect them together using this sequence theory. But to explain how to do this will take time, so we will do this next time, next Monday. So, but in total, yes, you will have 3 tasks for your homework.
We need to do all 3 at the same time, or we need to do
No.
first?
This is not quite important because you could do in any sequence,
Oh.
but you need to complete all 3 tasks. Yes, this is the issue. Okay, so for today, this is all. Next Monday, we will continue. Maybe you will have some questions, and I will explain you about the logic, the main ideas, how to do this first task. And this document you will have in Orcus. Yes. Professor will add
I
this.
hope.
Yeah, this document to
Okay.
Orcus. Yes. So that's all for today.
Thank you.
Bye.
sequence.